Inside Silicon, the technology behind everything. Powered by Semionics.
You know, it feels like we're constantly hearing about the next big AI breakthrough. But behind all that code, behind the algorithms, there's a physical story. It's a story about the very foundation of this whole revolution and a quiet crisis that could define its entire future.
Just think about it for a second. Every single large language model that's out there writing poetry or, debugging code. Every self-driving car that's trying to navigate a super complex street. All of that intelligence, all of that stuff that feels like magic.
It all depends on silicon. Yep, these tiny, incredibly intricate slices of engineered sand. It's so easy to forget, right? AI doesn't really live in the cloud, it lives on physical chips. And right now, the rules for building those chips are being completely torn up and rewritten.
So that brings us to the most crucial question of all. What happens when the very material that powers this entire revolution starts to push back? What if our current way of building AI's brain is just running out of road? Okay, so to really get this, we first have to understand why AI is such a demanding and honestly kind of weird workload for a traditional computer chip. It just doesn't play by the old rules. For decades, we designed CPUs to be like a Swiss Army knife, flexible, pretty good at a lot of different things. But here's the thing. AI doesn't need a corkscrew and a tiny pair of scissors. It needs to do one core thing. Basically the math for finding patterns in data, billions and billions of times, all at once. It needs a specialized super tool, and that's exactly why we've seen this huge rise of GPUs and other AI accelerators. But this specialization, it creates a new, massive problem. And surprisingly, it has less to do with the actual computing and everything to do with logistics. The real challenge, the real tyrant, is just moving data around.
This slide it completely flips our intuition on its head. I mean, look at this. On a modern AI chip, a staggering 62% of the energy is spent just moving data from memory to the processor. Only 38% actually goes to the thinking. That's like having an office where your workers spend most of their day just walking back and forth to the file cabinet instead of actually doing their jobs. It's wildly inefficient.
And this inefficiency, this bottleneck, it actually has a name. People call it the memory wall. And it is the single biggest villain in our story today. The processors are screaming fast, they're ready for more work, but they're stuck, just sitting there waiting for data to arrive. So how in the world do you break down that wall?
Well, you get creative. You stop trying to build one giant, perfect, monolithic chip, and you start thinking more like you're building with high-tech Legos. This is a fundamental, ground-up revolution in how we assemble the brains for AI.
So say hello to the chiplet revolution. The idea is, instead of making one huge, complex chip where a single tiny flaw can ruin the whole thing, you design smaller, specialized little chiplets. You can make these tiny pieces with much higher success rates, and then you just assemble them together into one super powerful package. And this is exactly why this chiplet approach is winning. I mean, first, it's cheaper because you throw away fewer failed parts. It's modular, which lets you mix and match the best chiplet for memory with the best one for computing, even if they're made using totally different technologies. It's really the ultimate in custom, high-performance design. Now, this whole move towards chiplets, it's part of a much bigger shift that's happening. For, half a century, the goal was simple: make the transistors smaller. But that game is getting impossibly hard and, frankly, impossibly expensive. The new rules of the game are all about being smarter, not just smaller. And if you want to know why, here it is. A single machine, just one, that's needed to etch the patterns for these advanced chips costs $150 million. That is just not sustainable. The brute force method of just shrinking everything is hitting an economic wall just as hard as the physical one. So, the crucial point is this.
The new benchmark for success isn't just raw speed anymore. It's efficiency. The big question that now drives all of silicon design for AI is how much computational power can you get for every single watt of electricity you consume? This slide really puts the whole evolution into perspective, doesn't it? In the past, it was all about the transistor. That was Moore's law. Right now, we're in the era of the system, thinking about how we package things using chiplets. And the future? Well, it's going to be memory-centric, finding clever ways to bring the computing and the data as physically close together as possible to finally, once and for all, tear down that memory wall.
And of course, this changes the kind of people we need. The hero of this story is no longer just the person who can design the fastest circuit. It's the silicon system architect, someone who really understands how all these different pieces, from power to packaging to memory, all have to fit together perfectly to build an efficient, powerful system.
Which brings us to the core takeaway of this entire explainer. We can dream up the most incredible, mind-bending algorithms, but at the end of the day, their potential is defined by the physical hardware we can actually build. AI's future depends entirely on these innovations happening in silicon.
So as we look ahead, I want you to remember this. The next great leap in AI might not come from a programmer in a hoodie, but from an engineer figuring out a totally new way to package tiny pieces of silicon. The future of AI isn't just being coded, it's being built. And after we conquer the memory wall, you have to wonder, what physical limit is coming for us next?
Inside silicon, the technology behind everything. Powered by Semionics.